Dale. In this video, we're going to work on solving systems of linear equations. We'll look at both 2 and 3 variable examples, and we're going to look at 2 different methods of solving: substitution method and elimination method, also sometimes called addition method. We are not going to use graphing as a method for solving, but it is good for explaining why there's 3 possible outcomes that can happen when we solve a system of linear equations. What a system of linear equations will be is we're going to have equations for 2 lines. I'll just make up a couple here. These are just nonsense, so they don't apply to this picture. But something like that. And if we have 2 lines and we graph them, one of 3 things can happen. The 2 lines could meet at a single point, and that would be one solution, and that the ordered pair that is that point, so like in this case 2, 3, that would be my solution for those 2 equations. Again, not really these 2, just showing 2 linear equations here. I could be given the equations of 2 lines and they are actually parallel to each other, so they have the same slope. If that's the case, they are never going to cross, and so that means they're not going to have a solution. The word for that is the system is inconsistent. For this one, where it's one solution that's independent, we don't use that one as much, but inconsistent we use pretty frequently to describe this system. When you solve, you're going to find that all the variables drop out and you're left with some kind of weird false statement like 0 equals 7. That's going to be the heads up that it's a no solution. We'll see that as we do some examples. And the last thing that could happen is they're actually the equation of the same line, but maybe one of them was a little disguised so you couldn't tell it at first. If they're actually the same line, when you graph them, they're right on top of each other, which means that every single point on that line is a solution to that system of equations. And so it has infinitely many solutions. The word for that one is dependent. So dependent goes with infinite solutions, inconsistent goes with no solutions. When you solve this, you'll eventually get to 0 equals 0, or something like 8x equals 8x. When you bring that over, then you're at 0 equals 0, but that's how that will look when you run into dependent systems. For our first method of solving is going to be substitution. It is the more limited of the 2 methods, and there are times when it's definitely the best way to go, especially when we get to nonlinear systems. Substitution can be really effective in certain situations. So what we do for this is we solve one of the variables in terms of the other is step 1. So in this case, x is already in terms of y, so step 1's already done. And then step 2, we do the substitution. So since x equals negative 5y minus 3, I'm going to end up substituting that into the other equation for the x. And then I'll have an equation all in terms of y, and I'll be able to solve. There we go. When we do that, we'll have y equals, and then we'll do what's called back solving, plugging that into, we can plug it into either equation, but this one's easier because it's already solved for x. So once we know y, we'll plug into here, and that's going to give us x. And then if I was going to be really diligent, I would then plug x and y into this first equation and make sure that it checked and came out to negative 41. But that's how you check, is to substitute the point into the equation you hadn't already used to solve. So let me show you what that will look like in practice. We're going to have negative 7, but instead of x, now we're going to let minus 5y minus 3 stand in for that x, and then minus 4y equals negative 41. And then we just have to solve that out. So that's going to be positive 35y, positive 21, minus 4y equals negative 41. 35y and 4y, so we can make that 31y. There's a plus 21 here, so I'm going to subtract that over to this side. That's going to be negative 62. Divide both sides, and y equals negative 2. So with that, we are going to do our back solve and take the negative 2 and plug it right here for this y and get x. So x equals negative 5 times negative 2 minus 3. X equals 10 minus 3, or x equals 7. So our solution set for this one is going to be 7 and negative 2. This next one is the same idea, except initially neither of these equations are solved in terms of x or y. Looking at it, to me, the easiest one to get alone would be that x. I would just subtract the 4y over to this side and go 9 minus 4y is equal to x, and then I can plug that in for the x of the second equation. So negative 8y is going to equal negative 18 plus 2 times, this is what we're substituting for x, 9 minus 4y. Distributing, we're going to get plus 18, and then that'll be minus 8y. Minus 18 plus 18, that would be 0. So now I have minus 8y equals minus 8y. And you can see these two sides, these are equivalent to each other, they're the same, so it's going to be the dependent one. If I add the 8y over, I'd be at 0 equals 0. So this system is dependent. Just a note, so here I solve for x. I could have solved for any of the other 3 variables as well. That one just seemed the easiest. I wouldn't necessarily want to get this into y equals, which sometimes I see students do. If you did that here, you'd subtract the x over, and then you'd divide everything by 4. You'd have negative 1/4 x plus 9/4 that you would have to work with, and that would be so much harder than what we did. So the goal for that step is really to try to keep it as easy as possible. Likewise, the goal for this whole section is really to try to keep things as simple as you can. You'll see that more in this next method. So next up we have the elimination method, which is also sometimes called the addition method. What we're going to do is we're going to add these two equations together with the intent of eliminating one of the variables. So that's why it's called both addition and elimination method. When we do that, the things that we can do are we are able to multiply equations by a constant. So for instance, if I wanted to multiply this side by 5 for some reason, that would be perfectly fine. As long as I did the same thing on this side of the equation, I can multiply that by 5. So what our goal is going to be is to get where we have the same coefficient for one of these variables, but with the opposite signs. And that's kind of, I'm just talking through what this box up here says. So with the 4 and the 3, I can either make them a 12 and a negative 12, or with the 5 and the 10. And really we're thinking what's the least common denominator if we're thinking in terms of fractions. That's the number we're looking for, is the smallest number I can turn both those into. With 5 and 10, I can make this 5 into a 10 by multiplying this one by 2. So that has less steps, so I'm going to pick that version. We often label our equations, so let me do that. I'm going to just call this one equation 1, this one equation 2. And I'm going to multiply equation 1 by negative 2. And that's going to give me a plus 10y here, which will cancel out with the minus 10y. So multiplying, we get negative 8x plus 10y equals, that would be a positive 2. If you're looking for errors when something's not working, check this other side of the equation. That is very often where it is. And then I'm just going to add to that equation 2 just as it is. So 3x plus 10y equals 18. Oops, I wrote down the wrong sign right there. There we go. So notice plus 10 minus 10, that's what we wanted that to do, is for those to just cancel. And I have negative 8 plus 3 would be negative 5x. And then on this side, those are gone, and then this would be 20. And then dividing the 5 over, we have x equals, negative 4, excuse me there. Once we've found negative 4, we can do the substitute back into the original equations, and we'll solve for the other variable, which in this case would be y. So I arbitrarily picked the first one, so I'm going to go 4 times negative 4 minus 5y equals negative 1. So that'd be negative 16 minus 5y equals negative 1. Add the 16 over. Negative 5y would equal 15, and y is going to be negative 3. So solution set's going to go -4 and -3. This next one, 2's and 3's or 6's and 9's. 2's and 3's are smaller numbers, so I'm going to work on those, and you'll see here in a second it wouldn't have mattered. But just sort of at a casual inspection, I would pick the smaller numbers. So again, we'll have equation 1 and equation 2. I'm going to go -3 times equation 1 because I want to get one of these signs flipped around. I'm going to make them into 6's, but I want one to be positive and one to be negative. So -3 times -2 would be 6x and then minus 18y equals, that would be positive 48. And then down here I'm going to go 2 times equation 2 to get a -6x. And then I'll get a positive 18, and that would be a -56. And if you look over here, these are all canceling out. Everything's dropping out. 6 minus 6 is -18 plus 18. So that side is 0. And then this side, instead of being 0 like the last one, it is -8. And so this time I got a false statement, so that means that this system is inconsistent. Next up we have 3 equations with 3 unknowns, and so instead of being two-dimensional graphs, we have planes in space, so it's 3-dimensional. We have the same 3 outcomes. If we had 3 planes intersecting, they could intersect at one point, like this one. They could intersect in a line, like this one, and when it's just one point, that's where there's one solution. When it's a line like that, that's where it's dependent, and would have infinite solutions along the line. Or we could have where the planes never did have a point in common, lots of different ways, and that would be inconsistent. So when we're solving these systems, and it's all written out in the notes, what we're going to do is we're going to eliminate the same variable twice. So I chose to do x in the notes. For this one, you can make a good argument for y or z as well. Any of those would have been not too hard. The example after this, they're all kind of hard. So I'll show when the numbers are a little more difficult too. But with this one, I'm going to eliminate x twice. And so I can use equation 1 and 2 together. I can use equation 1 and 3 together, or I can use equation 2 and 3 together. And I want to eliminate x twice so that I have 2 equations left in just y and z. Once we get it to there, it's just like one of these. The rest of it is everything that we just did in that problem. If I have 2 equations, I can solve those together, get my first answer, plug that in, and get my second answer. And then the only difference down here is that I will plug both of those into one of these and get the third answer. But the first step is to eliminate, has to be the same variable, so your 2 equations left have the same variables, but we're going to eliminate it 2 times. And so again, y and z would have been totally good choices on this one too. I happened to pick x. And so I did -2 times equation 1, and then I'm going to add to that equation 2. So I'll have a -2x to plus 2x right there. So that's going to start off -2x and then plus 6y minus 2z equals 6. And then I'm going to copy this one down. And then we'll add those together and we'll eliminate x. And I'm going to call this one equation 4, just to give it a name so I can refer to it later. So those drop out, and over here I have 8y minus 4z equals 20. And then I did -1 times equation 2 and added that to equation 3. Again, there's an infinite number of right ways to do this, so there's nothing special about what I'm picking, other than it didn't seem super difficult. So there's there's my first equation. Oops, this is actually this should be 2. And then I'm going to add to that equation 3. And the x's drop out again, and that's the plan because I need both these 4 and what's going to be equation 5 to have the same variables so that I can eliminate one of them in the next round. So it's going to be a y plus 4z equals negative 11. Oops. And once I have that, like I said, now we're back to that last, there are 2 questions ago where we have 2 equations and 2 unknowns, and I can just solve those. For 4 and 5, gotta like the z's are already set up, minus 4 and plus 4. So I'll just sneak over here with it and go 8y minus 4z equals 20. And for equation 5, we got y plus 4z equals negative 11. And that's going to be 9y. Those cancel, and then 20 minus 11 would be 9. And so it looks like y equals 1. So that would be my first answer. I can go back to either equation 4 or 5 to get my next solution. I'm going to go to 5 because it looks easier. So that would be 1 plus 4z equals negative 11, subtracting 1 over, 4z equals negative 12, and z equals 3. Now that I have y and z, I can go back to any of my first 3 equations. I bet I picked the first one. I did. And then I can plug in this y and this z, and that will let me find x. So we'd have x minus 3 times 1, and then minus 3 equals negative 3. So x minus 6 equals negative 3, and x equals 3. For these ones, we have 3. It's an ordered triplet instead of an ordered pair, and it goes x, y, z alphabetical, as you'd probably guess. And so 3, and then 1, and negative 3 are our solution set. This last example is the exact same thing, except it's just worse numbers. So I would do one example where the numbers are a little bit harder. Don't like the z's. So the z's, I'd have to do a fair bit of work to eliminate those, just kind of by inspection. I can make these into 10, I can make these into 15, I can make those 2 into 6, but I'm having to do like a lot. I'm having to do as much as I can to each equation. The y's aren't terrible. I could do this by 4 and eliminate that, and I could do this one by negative 6 and eliminate that. Or with the x's, the 3's, I would just have to do a negative and it would eliminate, and then I'd have to do a 3 and a 4 with one of them negative to eliminate, make this into a 12. Again, I picked x, but y isn't a bad choice either. Wouldn't pick z. That would be my last one I would choose. So let me do the hard one first, and I'll do 4 times equation 1. So then that will make where I have to do negative 3 to equation 2, because I want them both to come out 12, but with opposite signs. So 4 times 3 is 12x, and then plus 24y, plus 8z, and 4 times 30 would be 120. And then that would be negative 12x, and then plus 12y, and then plus 15z, and then times negative 43 would be 129. And then we'll add those together. X's drop out as planned. That would be 36y. Oops. Plus 23z equals 249. And that is equation 4. So then we'll do, I did 1 and 3 together, and I did negative 1 times equation 3 just to get those signs flipped. So let me get that written out. So equation 1, 3x plus 6y plus 2z equals 30. and then the negative of equation 3, or negative 1 times equation 3, would be negative 3x minus y. That would be plus 3z equals, and then I'll flip that to a positive 10. Those cancel. 5y, 5z equals 40, and that is going to be equation 5. So now looking what I have to work with, these are pretty terrible. I got 5 and 36, or 5 and 23. There is one sneaky thing that I can do, which is simplify this equation a little bit. This wouldn't always work, but if you notice, everything is divisible by 5. So I'm going to multiply this by equation 5 by 1/5, and that will turn this into y, because 1/5 of 5 makes a 1, plus z equals 8, and that's going to be a lot easier to put without equation 4. So I'll roll up here a little bit. So now I'm going to just copy down equation 4. So it'll be 36y plus 23z equals, oops, that doesn't look very good, 249. And then I'm going to multiply equation 5 by negative 23. So when I do that, we'll get negative 23y minus 23z. Let's get rid of that. And I picked the 23 because it's a smaller number. And then what does this come out to? 8 times the 23 would be negative 184 on this side. And so subtracting there, we're going to get 13y. And then on this side, we're going to get 65. And then kind of miraculously, y equals 5. So definitely harder when the numbers are a little bit bigger, but it's the exact same process. From here, we'll plug y in right there and get 5 plus z equals 8. Subtract the 5 over, and z equals 3. And then I went back to equation 3, which I'll scroll down here and do that. So equation 3 was 3x, and then plus y, so plus 5, minus 3 times z, so that's 3, and that equals negative 10. So cleaning that up, we'd have 3x, 5 minus 9 would be minus 4, equals negative 10. Add the 4 over, 3x equals 6, and x equals negative 2. So final on this one would be negative 2, 5, and 3.